Hello, I'm Heikki Linnakangas. I've been working on Postgres and traditional databases for a long time. Today I'm going to talk about the vector data and how vector data is different from other kinds of data. So my background in pgvector and vector data in general is only since about last autumn. So I started to look at pgvector source code from the point of view of someone who knows how traditional databases and data types work. So I dove into the code. I didn't pay much attention to how do you actually generate vector data or how do you generate the data that goes into the database. That's not so interesting to me. But I looked at how Postgres and pgvector deals with this data. So one of the first things I found, like looking at the code, is this little snippet. This is a piece of code that runs whenever you're building an HNSW index with pgvector. This is code pretty deep in a pretty tight loop, so this runs hundreds of times for every tuple that you insert, like every vector that you're inserting. And I was thinking, HNSW index build was pretty slow, so I was thinking, how do you make that faster? And one thing that immediately stood out to me was that if you're doing a lot of allocations, look, there's 3 allocations here in a tight loop, so that has got to be very expensive. Or so I thought. And I have a lot of experience with B trees and traditional index types, so I thought, that's got to be the problem. It turned out that it really didn't matter. With HNSW, it's such a more expensive algorithm than regular B trees and stuff that those 3 allocations, they were just lost in the noise. I actually wrote a patch to fix them, like remove those allocations and make that faster. But again, it didn't make any difference. It was like a couple of percentage points of the overall CPU time because there's just so much other stuff going on. So that was kind of my first lesson on vector data. First lesson was that these indexes and these algorithms are pretty expensive. They consume a lot of CPU. And what you might think from regular B trees or other index types, the knowledge isn't applicable with these algorithms. They are different. So what is a vector anyway? If you go back to high school maths, you might remember that a vector is it's basically it has multiple dimensions, and each dimension has a magnitude. Like how if you think about a 2-dimensional vector, for example, it has an x-axis and y-axis, but it can have any number of dimensions. So at the database level, a vector is stored as an array of floats, basically, an array of floating point numbers. The number of dimensions that you have and what those dimensions actually mean depend on the use case and how you generated those vectors and what you're trying to do with them. For example, if you're using OpenAI, it has these language models with 1,536 dimensions. They have other ones with different amounts of dimensions. And in those models, the dimensions are kind of hard to imagine what they even mean. But what you basically just do with them is you compare them with each other, and and it depends on the model you're using. So one thing to note here is that each of these floats is stored as a 32-bit floating point number. So if you have 1,500 dimensions, that's over 6 kilobytes of data just for each vector. So that's a pretty large chunk of data if you compare it to a single integer or some simple data types or even text. So that was kind of my second lesson when I started to work with these vectors. They're pretty large. 6 kilobytes of data for each tuple, each value in a column is pretty large. Postgres has a limit of 8 kilobytes per page per physical page, and 6 kilobytes is actually pretty close to that. If you have a piece of data that's larger than 8 kilobytes, then it gets what's called toasted in Postgres. So it actually gets split into smaller slices, and they're stored out of line, like not in the main table itself. So that typically happens with vector data. They get toasted and stored in a separate what's called the toast table. Postgres can deal with that, but it can affect the performance in, depending on what you do, that is either what you want, because you don't want your vectors to be part of the main table, because that speeds up queries on the main table if you're not accessing the vector. But on the other hand, if you are reading the vectors, then it can slow that down. So what's the big deal really with vectors and being large? I mean, we have other data types that are also large. For example, you can have just text documents, or you can have binary blobs. The difference with that is that with the text document, you just store it in the database and you can retrieve it back, but you're not typically doing any queries on those large documents or binary blobs if you're storing images or such. You're not really doing any queries on them. There is full text search, but that works slightly differently. In full text search, you index each individual word or fragment of a word, but not the whole document as such. You're not really pushing around the whole document. Except if you do want to do some kind of smarter search on text documents, what you would actually do is to create a vector out of that text document, and then now you're kind of back to square one, and that you're dealing with vectors. Saying if you want to index images in Postgres, what you would actually do is that you index the vector that represents the image, and now you're back to square one with a large vector. JSON is another interesting case. JSON documents can be quite large. But what you actually do with the JSON document is, again, you don't index the whole document as such. It's not very interesting, but you split it into smaller key value pairs and you index those with the GIN index, for example. But that strategy doesn't work with vectors because in the vector search, all of the vector dimensions need to be searched together and considered together. You don't get just pick one of the dimensions and index that. So I mentioned vector search. What is vector search then? It's basically all about the nearest neighbor search. So you have an input query that is represented by one vector, and you have a lot of vectors in your database, and you want to find all of those vectors in the database that are similar to your search vector. And your query typically looks like this. You do select star from a table. You might have some extra filters there or something, but then you do order by the distance from your query vector. And you need to have a limit, or otherwise you're just going to return everything anyway. For example, here's an example query where I use the DBpedia, which is like Wikipedia articles database. This is a common example used in a lot of blog posts about pgvector, so I use the same one. If you're looking for all of the articles that are similar to parabolic reflector, you might run a query like this, and you might get results like that. And you can see the order by distance there and the limit. So isn't this very similar to how we're dealing with geospatial data? I mean, Postgres has, or there's an extension called PostGIS, which can deal with geospatial data. And even built-in Postgres has a point data type, and you can do nearest neighbor search on that. And the query, if you look at this geospatial query down here, I mean, that looks very similar to what you saw in the previous slide, which was it's a similarity search. Like you have an input point in this case, which you can think of as a two-dimensional vector, really. I mean, it has x, y, and y coordinates roughly. And you do a nearest neighbor search, so you wanna find the points that are close to that. So this looks very similar, right? So what's the big deal with vectors then? Is because we have had geospatial data for a long time, and you can deal with that just fine. Well, the basic difference is that the vectors just simply have a lot more dimensions. In maps or geographical data, you have 2 dimensions, 3 maybe, if you're dealing with the sphere like an Earth or some other system like that. But these vectors that you create for OpenAI stuff, like AI stuff or image search and applications like that, you have hundreds of dimensions or thousands of dimensions. And it turns out that the traditional approaches that you use to deal with geospatial data, like R trees, KD trees, partitioning, among some of the axes or some of the dimensions, they kind of stop working when you have so many dimensions. So you need different algorithms to do vector search. So this is, and I went through this thought process myself. Like, can't you just use one of these approaches? And no, you cannot. The thing is that there's a phenomenon called curse of dimensionality, and I recommend to look it up on Wikipedia. But what it basically says is that many of these algorithms, especially if you're calculating the distance between 2 points, the distance metric kind of breaks down when you have more than 2 or 3, or maybe a handful, maybe let's say more than 10 dimensions. and the distance metrics kind of stops making sense. And I'm not going to try to prove that. I recommend to look it up and read the Wikipedia articles and other resources on that. But basically, one way to think about it is that your intuition of how the world works in higher dimensions is just wrong. It's very easy for humans to think in 2 dimensions, like, you have a flat surface and you can see all of the points there, or in 3 dimensions because our world is 3-dimensional. Maybe you can deal with the 4th dimension as a time, but if you try to go beyond that, like it's just impossible for a human to kind of. What does a sphere in 1,000 dimensions look like? It doesn't make sense to a human. And because of that, your intuition of how the algorithms and stuff works with the higher number of dimensions is just wrong. If you look at any of the papers on graph algorithms or vector search algorithms, you will see pictures like this one. This is from an HNSW paper. It's the first one I happened to find. And it's mapped as a 2-dimensional levels or layers. But it's important to realize that this is just a very flat approximation, because in reality, you would have thousands of dimensions here. And it just doesn't kind of fit in a human brain. So forget about it. Like, just trust the curse of dimensionality and smarter people who have done the research. These traditional algorithms that work fine with 2 or 3 dimensions, they don't work with higher dimensions. So one upshot of this is that, unfortunately, there are no good algorithms to do accurate nearest neighbor search in higher dimensions. But what you can do is what's called approximate nearest neighbor search. And therefore, all of these algorithms that deal with vector data, they are in fact approximate nearest neighbor search algorithms. They will not give you exact results, but you always have to kind of make a trade-off between recall, which means like how accurate is it, and speed. How fast is it to search? How fast is it to create the index? How much work are you willing to put into getting better, more accurate results? And if you're willing to accept that you're not going to get the exact results, but the approximate results, these algorithms work pretty well, but it is something to keep in mind. For example, here's one query from the same data set. And you can see that even though there is an order by distance, if you actually look at the numbers carefully, there is a problem there. Like, the distance of some of those things are marked here in red. Those rows are actually not in the right order. If you run the same query, but you disable the index scans, you would get the correct result. But then it takes a lot longer. Here's another very typical case. People run into this all the time, and there's discussion on various approaches to fix this problem. But if you do a query and you add some filter, like in this case, you will have an extra condition that the title must begin with an A. The way the HNSW search will work, it will first find a set of results and sort them in the right order, and you do the filtering only after that. And it might actually not give you all of the results. So clearly, with the result here on the left with the index scan, like, that's incorrect. Like, you only get one result back, whereas on the right side you can see the correct result with the sequential scan there, and the index search just leaves out a lot of the details. So that's just something to keep in mind when working with these algorithms. And like myself, I've been working with databases for a long time, so it takes a little bit of getting used to that your query might actually return incorrect results, and just be cool with that. I think there would be stuff we could do in Postgres side to deal with this better. Because one consequence for this, for example, is that the planner might make like wrong choices or bad choices with the rest of the query plan. So if you have a complex plan and some part of that plan is using an index like this, and it doesn't return all of the correct results, but an approximate result, that can really screw up the rest of the plan. There isn't any great solutions to that, but like one workaround can be that if you put your vector search in a with clause, that can actually help, and it's easier to think about anyway. Like, do the vector search separately as a separate part in the query, and then you add the additional filters and other conditions after that. at least it might not be the fastest way to do it, but at least it will, where the inaccuracies are coming from, at least in that way. So that's just something to keep in mind with vector search. It's not accurate, it's inaccurate. So vector search algorithms can be categorized into roughly 3 families of algorithms. There's cluster-based, which is the basic idea with cluster-based algorithms is that you try to find groupings of different vectors or different tuples, and you create a list of maybe 1,000 different lists or 1,000,000 different lists, list of clusters, and then you clump together all of the similar stuff that is similar to that cluster in that list. That's one approach, and pgvector implements IVF flat, which belongs to this family of algorithms. Then there's graph-based. These are slightly newer algorithms. HNSW is the very common one, and that's the one also implemented by pgvector. There are others like disk ANN, but it's the same kind of approach. You have a graph, and you navigate that graph until you find the ones that are similar to your search. The rough trade-off between these algorithms is that the IVF flat is much faster to build, like it's relatively fast to build, but it's slower to search and provides less accurate results. The graph-based algorithms are slower to build. It takes a lot of memory, a lot of CPU to build, but they're very fast once you build the index, and they get pretty accurate results. One thing to note is that HNSW index build is an in-memory algorithm, and this is what I was looking at when I said that when I started to look at pgvector back in autumn, and I showed the piece of code with a lot of allocations. That was from HNSW index build. So it's very memory hungry. It basically assumes that the whole graph, the whole index fits in memory. And in Postgres, it better actually fit in what's called the maintenance workmem. Like that's an allocation, a piece of allocation that you do upfront when you start to build the index. So it's very important that you tune the maintenance workmem correctly. It has to be basically large enough that your index fits in that memory. If you don't tune the maintenance workmem, then pgvector will actually give you this warning if you're trying to build the index and it doesn't fit in memory. It will still try to soldier on and build the index, but it will take a long time. So you probably want to abort the index build at that point. Increase the amount of memory, like set maintenance workmem higher, assuming you have the RAM, and then try again. Searches are also pretty memory heavy. Like the same HNSW actually uses roughly the same algorithm for searching and inserting, like building the index. So even searches actually do like hundreds of random accesses all over the graph, which means like hundreds of pages are accessed for every search, which can be very slow if it doesn't fit in a RAM. So there are a few different approaches to this. At Neon, we are building something that like auto-scaling, which helps with this because you can have a large instance when you start to build the index, and you give that enough resources that you finish that quickly and you have enough RAM, and then you can shrink it down when you're doing the searches and you don't need such a big machine. I know there are some projects out there where you would use a large cluster or like a different instance types to build the index. You would ship the work of index build to a separate machine, and then when the index build is done, you just load it into the main database. That would be another approach of having the resources available at index build. But in general, the rule is that you need to have a large enough instance type when you're building the index that it fits in RAM. Otherwise, you will probably run out of patience. What this also means is that the amount of data that you can deal with is actually typically limited by the amount of memory you have. Like if you have billions of rows, in practice, you need to have a machine that has enough RAM to fit the whole data set. That's different from other data types in Postgres or in databases in general. Like Postgres can easily build a terabyte index or a B-tree index, even if you only have a gigabyte of RAM. It will just take a little longer, and sure, having more memory helps, but there are very efficient external sort algorithms that can build that index fast, even if it doesn't fit in RAM. But that's not the case with vector data. You are really bound by how much memory you have available. So some of the big advantages of or new stuff that came out in pgvector 0.7.0 version is new data types to specifically to address this problem, basically. So because you are bound by the memory size, if you can just make your vector smaller, that helps. You can fit more of them in the same amount of memory. Again, that's kind of true for any data type in Postgres and in database in general. Like if you can make your database smaller, that always helps because you have less data to deal with. Like you can fit more of your data in memory. It takes less time to warm the caches because there's less data to deal with. It makes your backups go faster because they're smaller. It makes restore go faster because it's smaller, and kind of the database size is a multiplier for all of the other things. But with pgvector, like with vector data, it's especially important because it kind of your performance will go off a cliff if it doesn't fit in memory. So you have to make it fit. So the new data types in 0.7.0 are half-vec, which is basically an array of 16-bit floats, where the traditional vector data type is an array of 32-bit floats. So you lose some of the precision in all of the dimensions, but it makes the data a lot smaller, like half as big, basically. So that allows you, roughly speaking, to deal with twice as large indexes with the same amount of RAM. There is also support for indexing bit vectors, which is a bit string, like just 1 bit per each dimension. So that's obviously a lot smaller than the vector or even half-vec, like 1/32nd piece, 30th of the size of a 30-bit float. But that loses quite a lot of the precision. So it really depends on where your vectors are coming from. If they're still useful, if you reduce it down to 1 bit per dimension. If it does work, then great. I mean, that will make everything go much faster. But you probably want to experiment with that and see what works basically for your use case. Then the third one is called sparse vec. So the basic idea of that is that if your vector data has a lot of dimensions, but most of the dimensions are 0 in any particular vector, then sparse vec will only store the non-zero dimensions. So again, depending on the source of your vector data, like for how do you build your vectors, that might be a big win. So I have an example here of the half-vec data type, for example. You can see that this is the same data set I had with the queries earlier. The index build with the regular vector type took almost 7 minutes, 6 minutes and 42 seconds here. But with the half-vec, it only took 5 minutes, 14 seconds. So the time to build the index, it didn't quite go down to half the time, but it took like a quarter of the build time. And I think that's mostly because the operations are somewhat faster with smaller floats. And also, just because you have less data, it means that you get more benefit of caches. Like your CPU caches are more efficient. You can fit more data in your caches when the data is smaller. If you look at the size of the table, like you can see that it is, roughly half the size of the original table with the regular vector type. So that's the summary. My lessons when I've been working with vector data is that vector search is expensive and the vectors are large. And also they're large and they also need to fit in a RAM to really be able to deal with this data. And also vector search is approximate, so you have to take that into account, and you have to get used to that if you are a traditional database guy who doesn't like incorrect query results. With vector data, you just kind of have to get used to that. That's all I have. Thank you.